So this slide is an illustration of cell delays from an actual standard cell library. And I picked a 2-input NOR gate from the library. And I specified an input transition time of 80 picoseconds. That means you just imagine that one of those inputs is tied to 0 and the other input is transitioning, right? It is important that the non-transitioning input is at 0, because if it was at 1, then obviously this NOR gate will not, the output will not switch. So so just imagine that one input is at 0 and the other input is transitioning, and the transition time of the transitioning input is 80 picoseconds. Okay, and the output capacitance I have specified as 80 femtofarads. So we have very specific conditions here. Output is 80 femtofarads, output load cap, input transition time is 80 picosecond, and we're going to look at what the delays for this cell are in the standard cell library. So the table on the left is a delay from A to output. So you have to imagine that B is at 0, A is transitioning, and the table on the left tells us what the delays are from A to Y. Okay, Y is the output. When the output capacitance is 80 femtofarads and A is transitioning with 80 picoseconds. And what you see here is in this library there are multiple 2-input NOR gates with different drive strengths. So how many are there? There's XL, X1, X2, X4, X6, X8. Right? So 6 different drive strengths. XL, L represents low drive strength. Then there's X1, X2. That 1, 2 is just a nomenclature. It doesn't necessarily mean anything very specific other than the relative drive strength. Okay. And you can see in this case that we have 2 different delays for rise and fall from A to Y, and the difference is quite significant. So if I look at an X1 drive strength, when A is transitioning, if A is rising, if the output is rising, okay, when the output is rising, the delay from A to Y is 0.8 nanoseconds, and if the output is falling, then the delay from A to Y is 0.4 nanoseconds. So it's a big difference. So this is not a very well-designed cell in the standard cell library. In general, we prefer not to have such drastic differences in delays between rise and fall, but there will always be some difference. And in this case, the difference is quite significant. And basically, this cell is optimized for the fall transition. So the NMOS transistors in this gate are faster than the PMOS transistors because the rise delay is much higher. Okay. So on the left-hand side, you have a table for A to Y delays. On the right-hand side, you have the table for B to Y delays. So to assume that A is at 0 and B is transitioning, then what are the delays from input to output? And again, different drive strengths. You can see that the delays decrease in both tables. The delays decrease very significantly as the drive strength increases. Right? So it goes, for example, for the rise delay. If you take an X1, it is about 0.7. It's 0.795 nanoseconds in the table on the right, and it falls to 0.33 nanoseconds. So it's almost a more than 0.4 nanosecond decrease in delay from input to output as the drive strength increases. Okay. And you can see that the rise and fall delays are different, and the delays from A to Y are different from the delays from than delays from B to Y. Okay. Very important to appreciate that there's a lot of complexity in cell delays, and there are a lot of dependencies. Not only is there a dependency on PVT, there's a dependency on load cap, on input transition time, on the type of transition with this rise or fall, and the delays are different from different input pins to the same output. Okay. Here are some examples of some interesting cells that you would typically see in a standard cell library. Like I said, there will be hundreds, if not 1,000, different standard cells, different logic gates in a standard cell library. Incidentally, standard cell is just another, you can think of it as another term for logic gate. And so I may use those terms interchangeably. And here are some examples of the kinds of logic gates or standard cells you would see in typical libraries. And I've just picked some examples of some more interesting or slightly more complex gates. So one very common kind of gate that you will see in a standard cell library is what is known as an AND or invert gate, AOI. So that's an AOI function. And there are different types of AND or invert gates. The ones I've shown two different types here. I've shown you a 4-input AOI gate, okay, on the left, and then a 3-input AOI gate. And an AOI gate is very obvious. The inputs go through AND, and then the outputs of the ANDs are OR, and then the output of the OR is inverted. Right? So that's an AOI. So it's basically an AND gate with a NOR gate. And you can see two different AOI functions. Similarly, you will have an OAI function, OR AND invert. There can be 4-input. There can even be 5-input OAI functions or AOI functions. And then, so I've shown examples of a 4-input OAI and a 3-input OAI. Okay. These are some examples of gates you will actually see in standard cell libraries, combination gates. And again, sequential gates, like I said, they can have D flip-flops with various of different flavors, including multi-bit D flip-flops. So, a multi-bit D flip-flop is like combining two flip-flops into a single standard cell. So it has two D inputs, two Q outputs, and that independent inputs and independent outputs, they are in the same logic, sharing the same clock. Okay. So usually a 2-input multi-bit flip-flop or a 2-bit flip-flop will be the same logically as two 1-bit flip-flops, except it'll take less area. Okay. And area is very, very important factor in designing ASICs. Now, to use standard cell libraries, you need to have standard cell. You need to have data of the standard cell libraries. The information of every cell in the library needs to be provided in order to be able to use the cell in implementing a logic circuit. And this information for every standard cell is organized into various files. And these various files, we often refer to them as views. Okay. So the information about the cells in a standard cell library is organized into standard data formats of files, and these are often called views. There are two important views needed for the backend design process. One view is called a liberty view. It's a format, it's a standard format. We sometimes also refer to it as a .lib view because of the .lib suffix used in the names of liberty files. Okay. So the liberty or .lib view is one important view. It contains some important information about the standard cells, which we will review in the next few slides. But that's one view. And the other important view is what is called the library exchange format or LEF view. Okay. So these are two important views that I want all of you to get intimately familiar with as in the course of this class. And these two views or these two file types contain the information that is needed in order to use these cells in designing an ASIC. There are other views also that you will get with the standard cell library. There is obviously a Verilog view, which has a Verilog model for every standard cell. And this is needed in order to, for example, use in order to do logic simulation of the logic circuit. Again, there will be SPICE netlist views in case we need to characterize the standard cells or the logic gates. Like if you want to simulate the circuit of the logic gate to determine delays, then you would need a SPICE netlist view. And then there is what is known as the GDS2 view, which is a detailed layout of the standard cell. And that is obviously needed in order to create mask making data for the foundry. So let's start by looking at the .lib view or the liberty view. The information in the .lib view of a cell includes the following: the functionality of that gate. Okay, what is the functionality? Is it a 2-input NAND gate? Is it a 4-input MUX? Is it an AOI gate? That functionality is captured in the liberty view or the liberty file for the standard cell library. Okay. The liberty file or the liberty view also contains timing information. So if it's a combinational cell, then the input output delay, the output transition time, the dependencies of these delays and transition times on the load capacitance and the input transition time, all that dependency information is also embodied in the Liberty file in the form of either equations or timing delay models or just lookup tables. And if the cell is a sequential cell like a D flip-flop, then the setup time, the hold time, the clock to Q delay of the flip-flops, all the timing information of the flip-flop would be there in the Liberty or .lib view of the flip-flop. Then power information for the standard cell, what is the leakage power, the dependency of the leakage power on, let's say, on anything, on load capacitance or input transition time. Actually, the leakage power does not depend on those factors, but for example, short circuit power or switching power, the different power components, some of them will depend on, will have dependencies on output load and input transition time. So that information on power will also be in the Liberty file. Even the pin capacitances, the capacitances of the input and output, the inputs and outputs of the logic gate, that will be in the Liberty file. Now, as I said earlier, the delays and even the power numbers of standard cells are dependent on PVT. So there will be a separate .lib for each PVT combination. Okay. And this is because timing, power, and electrical characteristics change with PVT. So for various combinations of process voltage and temperature, you will have a different .lib file. Data in the .lib file is obtained by running SPICE circuit simulations. This is called cell characterization. This is done one time, and then from the output of these simulations, you get all the delay and power information and its dependencies, and then that is all captured in some kind of standard format in the Liberty file. Okay, so at this stage, let's maybe look at a real Liberty file. So I have a standard cell library that I will bring up, and I'm going to my Unix environment here. And let's look at a real Liberty file. So I am currently looking at the Liberty files of a library from standard cell library from a company called Skywater. And if I look at, I'm in the directory where the Liberty files are, and I'm going to list all the .lib files that are there in this library. Let's see what we get. You can see there are lots of .lib files for the standard cell library. That's because you have a different .lib for different PVT conditions. You can see, for example, here there's 1.95 volts, 100 degrees centigrade, and the process is FF. Okay, so PVT. P is FF, T is 100 degrees centigrade, V is 1.95 volt, and I have a .lib for that. So why do I call process FF? This is a very standard terminology for defining the P, the process dependency of the standard cell's characteristics. So when temperature and voltage are concerned, it's very easy to specify them because they're numerical quantities, right? 100 degrees centigrade is temperature, 1.95 volt is voltage. These are numerical parameters, easy to specify them. But what about process? Process represents a variation in the manufacturing process. It's not a numerical quantity, it's a qualitative quantity. It's not a quantitative parameter, but a qualitative parameter, process. And so the standard convention in the industry to represent a particular sort of process, quote unquote, value is using this terminology, FF, as you see here, okay? And then you'll see SS and you'll see TT, very common conventional terminology to represent the qualitative parameter that is process. And what this means is FF means the PMOS is fast and the NMOS is fast, meaning the process variations are such that the PMOS is fast, it is high current, and the NMOS is fast, it has also high current. And SS means slow. So the PMOS and NMOS, the process variation is such that the PMOS is a slow transistor, the NMOS is also slow. Slow means for the same voltage there is less current flowing. okay, less drain current. F means more drain current for the same temperature and voltage. S means less drain current for the same temperature and voltage. And T stands for typical. So typical or the target drain current for a given temperature and voltage. Okay. So because of process variations, the drain current varies, even though the temperature and voltage may be the same. The drain current may vary just because of variations in the process. And so that is represented by this terminology of fast, slow, and typical, or FF, SS, and TT. In principle, you could have a process, corner or a process value that is FS and SF and various combinations of FS and T, but that's usually is very rare to see that. I've never actually ever seen that, but in principle that is possible. In general, you will see in a standard cell library, there'll be .lib files for different voltages, different temperatures, and different process conditions as represented by FF, SS, and TT. Okay, so this is what you're seeing here, different .lib, same standard cell library. Now, what are the different, how many cells are in this library? Let's look for that. Okay, that's the first thing I'm interested in. So first of all, let me just show you, let's just look at how a library looks. .lib file, and you can see that .lib file, it has some header information that tells us what is the type of technology, CMOS, what is the delay model. So the delay values are organized in the form of lookup tables, which are with the functional dependency is on, let's say the output capacitance and input transition time. How does the delay vary with these? That data is organized in the form of lookup tables. That's what is indicated in the header section of this .lib. Okay, and then let's see the units of the various, the units are, the voltage unit is volts, the power unit is nanowatts, current unit is milliamp. Okay, things like this. And this particular .lib is for a voltage of 1.95 volts. Process is 1. So FF means, I guess they're calling it 1. And the temperature is 150 degrees centigrade. Okay, as you can see here. So that's in the .lib. And then you have all these lookup tables. You can see there's a lot of characterization data. And you can see that this, for example, let's look at some, let's see if I can find some timing value here. Let's see power numbers. I'm going to try to find, here you go. So cell fall. So the fall transition time. Okay, you can see there are lots of values of the time, and they're organized in the form of a lookup table. You can think of this as a two-dimensional table with columns and rows, and as represented by index 1 and index 2. So index 1 is, let's say, the output load capacitance, and index 2 is the input transition time. And for various combinations of load capacitance and input transition time, the actual delay has been simulated and the value entered into this .lib. Okay, so that's what a .lib or Liberty file looks like. And if you ever find yourself pursuing a career as an ASIC, back-end ASIC design engineer, then you will necessarily have to be very familiar with this. And if you get familiar as a part of this course, then that would put you in good position for jobs in the semiconductor industry. So let me now let's kind of explore this library a little bit. I'm going to see how many standard cells are there. So I know, for example, that in the format of .lib, all standard cells are, the data for any standard cell starts, the first line is the word cell. Okay, so in this Liberty file, which contains data for all the standard cells in the library, each standard cell's data is organized under a line called cell and the name of the cell. So I'm going to grep. Grep is a Unix command. I'm going to grep for cell, and I'm going to find, let's see. Let me pick a name first of a library. Let's just pick any one of these .libs at random. And I'm going to say grep cell followed by space, and I'm giving the .lib library. Now I want all of you to be very familiar with this grep command. You will need to use it as you do homeworks and so on. This is a fundamental Unix command that you should know. Grep basically looks for any line which has cell followed by a space. And if I pipe this to more, I will see all the, so these are all the cells in the library, okay? And you can see there's a AND or A2111. So this is some kind of complex logic gate. I'm sure there will be a NAND gate. Let's look for a NAND gate, for example, that all of you know what's NAND. Let me grab for, I don't know, is it called NAND? Yes, so you can see all the NAND gates in this library. 2-input NAND gate with drive strength 1, 2-input NAND gate with drive strength 2, and so on. Okay, and so this is how I find all the cells in the library. That's again. Let me just list them all out. So the way to do that is in Unix, I can use the Unix awk command, and I'm going to print the second field, which is this one. That's what I'm interested in. So I'm going to say print $2, because the first field is the word cell. The second field is this entire thing here. And the third field is just this curly bracket. So I'm going to print this $2, which is the second field. And when I do that, I just get all of these cells. I'm only interested in, let's say, getting this part here. Sorry, just getting this part here. I just want to get a list of that. So let me show you how to do that quickly. Printing $2. Then I will basically extract that information using some pattern matching. So if I do this, let's see if I get it. So here's all the standard cells in the library. And you can see that that I have, like, for example, this function A211110, I have 4 drive strengths, drive strength 1, 2, and 4 for that. If I look for buffers, let me look for buffers. I can see all the buffers that are there in this library. And you can see that I have buffers with drive strength of 16. So they're very high drive strength buffers. That's very common in a standard cell library. You will have very high drive buffers in order to drive large capacitive loads or to drive long distances. You can see different types of buffers here with different drive strengths. There are something called clock buffers. These are buffers where the rise and fall, the delays for the rise transition and a fall transition, those delays are balanced. So these buffers would be used for the clock signals. Okay, and so there are various types of buffers here. If I want to look for NAND gates, let's look for that. Let's do grep NAND. And I can see there are different types of NAND gates in this library. There are 2-input NAND gates. There are 3-input NAND gates. There are 4-input NAND gates, all with different drive strengths of 1, 2, and 4. There are also 2-input NAND gates where one of the inputs is inverted. I think that's what that B means. Okay. If I want to know what is the functionality of any cell in the library, I just have to look at this Verilog model. So let's look at that. Let's go back here. And I'm going to go into the Verilog. And let's look for see if there, let's see what files are here. And you can see there are for every type, every standard cell, there is a Verilog model. Okay, so let's say if I wanted, in fact, let's look at one of these more complex cells to understand what it is. So I'm going to say go back there, run my command again, and I see that I have this standard cell A2, this particular logic. What is this logic? How do I know what this logic is? Well, let's look for that in the Verilog. In the Verilog view, this is the Liberty view. We're going to look at the Verilog view. So let's go to Verilog. And let's see if I can find if I can find a Verilog model for this particular logic function. And here we go. So here's the functional model here, Verilog. We look at that, and I can see that this particular function is a 2-input and into a first input of a 4-input OR. And here's the Boolean expression for that. So you can find out what the logic, what the functionality of that particular logic gate in the standard cell library is by looking at the Verilog view. Okay. Even the Liberty view will actually have this functionality, but in the Verilog view is a little bit easier to kind of read it. It's actually put here in the as a comment. Okay, so it's easy. It's not necessary that every standard cell library will put this kind of nice information in the as comments. This particular Skywater library is doing it, and I know that. That's why I looked at the Verilog. Okay, so you can see that in a you can, if you have the Liberty file of a standard cell library, you can find out how many cells are there. You can find out what the different functions are. And as the last piece for today's class, let's look at the areas of these cells. First of all, let's see if they're even there in the Liberty file. Sometimes it is there, sometimes it is not there. So I'm going to look at the cells. And let me actually do a grep -n so I can get the line number where that cell is. And let me get all of that out. And let's say that, okay, line number 337 is this particular cell here. Let me grep for that cell. Grep for this cell in the same .lib. This is the .lib. I will grep for that cell name there. See where it comes. So it comes there. And let me grep with a few more lines after the matching line. So I'll say -a for after the matching line. Let's say I'm going to look for 10 lines after the matching line. So you can see that here is that cell in the .lib. That particular standard cell appears in a line here, and its area is 14.3. Okay. If I took a higher drive strength, so let's look at the drive strength 2 and see if its area changes. Right? Take drive strength 2 instead of 1, and let's see what we get. And the area is, you can see the area is increased. So of drive strength 1, the area is 14.38. For drive strength 2, the area is 15.98. And if you were to look at the timing data for these two cells in the .lib, you will find that the delays for this drive strength 1 are higher than the delays for drive strength 2, but the area is smaller. So if you need to use this logic gate, but if you don't need it to be very fast, then you can use a drive strength 1 to keep less area. But if you need it to be fast and have low delay, then you would need to use a higher drive strength at the cost of higher area. Okay, so with that, I will end my class for the day.